So yeah, this is a talk, a super nerdy talk about network and crypto and early phase tinkering and all kinds of stuff. Thanks for, man. Thanks for coming. I hack on compilers at a company called Igalia. We do mostly browser internals. So if you ship WebKit or you ship Blink or you ship Node or V8 or something like that, and you want to participate in making the web better for your use case and for everyone, let's get in touch and we can make it happen. We recently did the generators work in V8 and adapted the generator stuff that existed in SpiderMonkey to work with the new ES6 standard, and that was all sponsored by Bloomberg. So that's the sort of stuff I normally do. And this is not a talk like that, right? This is talk about crypto. And I'm not a cryptographer, and I'm not, super network engineer. I'm just, a tinker and a nerd. And so I thought that, I saw this paper, and I was like, damn, I got to play around with this thing, right? So this is to talk about that. So the context we're in is, the context of you got generals peeping in on your emails and your Google searches, and, if you search for the wrong thing, if you read the wrong thing, they'll send men with guns, right? This is what they did, recently with a mother that was searching for a new pressure cooker while the teenage son, as one does, was searching for the anarchist cookbook, and, they sent the SWAT team, right? So, this is just a freaky place to be in the world. And it's just, creepy and disgusting. And the thing it makes me think of more than anything is that Tom Waits tune, like, what's he building in there? He's got subscriptions to those RSS feeds. He's been hacking on MinimaLT. We're in his router, and we're in his phone. And you won't believe what we saw from the drone. What's he building in there? What the hell is he building in there? We have a right to know. It's like these assholes are looking at you, and the real solution, of course, is to smash the state and, overthrow the political systems that are, creating this reality we live in right now. In the meantime, as people who make the raw substance of the future, we need to make their jobs a bit more difficult, right? And so let's talk about HTTPS. HTTPS is, it can be fairly secure. It's seen a long, good life, and we'll see, even more. But if you are going to attack it, you have a number of vectors at your disposal right now that, you didn't have maybe, 5 years ago. You could do some serious cryptanalysis work on RC4 or something. You could, pay off the certificate authorities to issue you a rogue certificate. And you could use JavaScript, boop, boop, right, in the crime and beast attacks that we've seen recently. There's been recent talk that, some implementations of TLS have backdoors. But I don't think these are, the biggest vulnerability in HTTPS, because for me, it's HTTP, right? It's the fact that you can access services in an encrypted fashion or a not encrypted fashion, and often we're doing it in such a way that everything can be snooped on, right? So the biggest enemy to me of HTTPS is HTTP. And DJ Bernstein has a competition that he and some other folks are running to come up with a next generation stream cipher, and he quotes a number of disasters. And if you go visit this webpage, there's lots of interesting stories about crypto systems that just broke, right? And the worst kind of breaking is when you just don't get any crypto at all, right? And HTTP has that sort of side of things. So I want to do a poll. I always like doing polls in my talks. So how many of you use the EFF HTTPS Everywhere extension? Good job, folks. That's really great. But obviously, it's not all of you, and it's not even me, right? So how many of you ever use Google to search, using the normal HTTP thing? I asked this in the reverse way, so I'm confusing all of you, but I know I search sometimes, often, usually, actually, over just plain HTTP, and it's just, it's nasty, right? So there is actually a reason for this, though, and I think, you feel it yourself. And it goes down to, actual fundamental things about the internet. So I took a packet trace of my browser, which, I run Linux as any, tinker and hacker does, and I actually use Epiphany, which is a browser built on WebKit 2 on the GNOME system. So I'm super weirdo here, but it's a modern WebKit 2 build. So this is very similar to what you have in your browsers. So at 0 milliseconds, I did a get to HTTP to GNU.org, right? So at 0 milliseconds, we send out this SYN packet, right? And the SYN packet's saying, hey. And then 130 milliseconds, we get back a packet from the server saying, hey. It's exactly like when you pick up the phone. It's like, hello, hello. And from this, we can compute, in this particular situation, that I've got a 130 millisecond round trip time, or half of that would be the latency. And this is not going to go down. Like, bandwidths are going to go up, but this particular kind of latency, obviously this is a transatlantic one from my French home to the server in Boston, but it can't go down below a certain level. And that certain level is, if you were to take a plane, like a light-speed plane, your latency would be 45 milliseconds. So there is something at which you're not going to go down. And so after I get this SYNAC, I can finally send off my get me the page. Later on, I get the first packet in the result, and I can start to parse it, right? And so I realize, okay, I got some CSS and some JavaScript and all the things, and so I can't actually ask for anything else over this same connection. So I fire off 3, in this particular case, parallel connections. So 3 more SYN packets go out to GNU.org. I finally get the end of my request, like the end of the response, back at 410 milliseconds. And then in super sad panda mode, I finally get my parallel connections opened after I've gotten the first document, and only then can I make the other round trip necessary to actually start fetching the auxiliary resources. So I mean, this is our internet, and I don't know. This is half a second, and it's horrible. Yeah, so this is even not very many bytes. So it's not a bandwidth question at all. It's completely latency driven. And of course, with HTTPS, as we all know, it just gets much worse. So SYN, I get back my SYNAC, and I send off my client hello thing. Server comes back and says hello. We do the certificate exchange dance. In this particular case, and this just blew my mind when I saw it, for some reason we wait for the ACK for the server that it received our certificate exchange packet to then send another thing saying change cipher. And I don't know if this is a bug in my networking stack or if it's something more fundamental, because I wasn't intending to do a deep investigation on TLS in this particular case, but I don't know. This is a sort of multiple round trips thing to set up a secure network connection that it's really horrible. I can only start to send my request. I've been talking back and forth and wasted an entire half a second, right? I would have gotten the result before using HTTP, but I'm only now just asking for it using HTTPS to finally get back the result at almost a second in, and only now, only at that half a second, when I get back the first packet, which is somewhere in between this 583 and 764 milliseconds, are we actually starting to kick off the parallel connections, which do the same thing times 3. And this is why it's slow. Like, this is why the internet is slow, and it's fundamental. It's because I'm doing this SYNAC dance for nothing, right? For nothing. I'm saying, hello, establish me a connection, and it's not even secure. So there is room here for a protocol which provides properly implemented strong crypto, a phrase which you might recognize from the first Snowden interview, like that this is what works, right? Properly implemented strong crypto. That connects faster than TCP, right? Like that this is a possibility, so this is something that probably will happen at some point. And this particular talk is a kind of early technological preview. The preprint on this paper for MinimaLT, this new protocol, just came out in May. So it's early days yet, still making and breaking, but this could be a sort of future glimpse on the internet. So I want to talk about the 2 parts: the properly implemented strong crypto part and the faster than TCP part. MinimaLT uses the high-level NACL library. It's actually pronounced SALT. I always say NACL. From DJ and Tanya Lang, Hashbreaker and Hyperelliptic on the Twitters. And doing a fresh protocol actually can make things much more secure, because you can design things sensibly from the ground up. You don't have to include like a bunch of broken ciphers. You don't have to include the null cipher, the opportunity to make a connection in plain text mode. You can make sure that by default, your implementations of the crypto primitives are not vulnerable to these various timing attacks that we've been seeing recently. And I don't know, it's just like an opinionated, high-level base on which to work. And the SALT library has been out and crypto-analyzed a bit. And, still relatively new, but it seems like a solid thing. And on top of that, MinimaLT adds a forward secrecy layer so that if someone breaks into either side and manages to get all the private keys on the server or the client, they won't be able to decrypt previous connection. So that's what that is. And it's minimal latency, right? The equivalent of DNS, and MinimaLT includes a sort of equivalent to DNS, requires 1 round trip. And otherwise, 0, in theory. You can send your sort of hello packet, which opens a connection, and include the equivalent of the HTTP GET request in that first packet. So you don't actually need a round trip in the beginning. And furthermore, your connection can be, it's actually a tunnel. There are connections inside tunnels. Your tunnel can be persistent. It can live a long time. It can persist over IP changes. So you don't need to do some particular parts of the protocol setup every time you work. So you can start working at home, like reading your Twitters or whatever, and you get on the train, and as the GSM changes your IP, it's still persisting on the same tunnel without seamlessly changing you over IPs without needing the application layer to do recovery and reconnection logic. So it can make things a lot faster in that case. And in addition, so you're designing a protocol today. You have to base it on UDP or TCP, right? Otherwise, it doesn't get through the internet. And MinimaLT is based on UDP. It adds a reliability layer, so it's sort of equivalent to TCP's reliability. It adds crypto as well, so it sort of folds in what would be a TLS layer as well, so it packs them into one sort of layer violating protocol. But I think it comes with a lot of advantages, and it seems to be okay. It's also resistant to denial of service attacks, which is another important detail when designing. There's sort of a family of this kind of protocol coming out right now, and resistance to denial of service is one thing that all of them are struggling with. And MinimaLT seems to have a good solution, although there are some details we'll touch on a little bit later. And it's fast. It's really fast. It's really fast. When you're running full speed, you can saturate your multiple gigabit links, and it can connect at very high rates as well. So we'll poke at that. So there are tunnels and connections. Inside the tunnel, the first time you create the tunnel, you have one connection. It's connection 0. It's a distinguished connection, and that's the one that actually allows you to create other connections. So you would make your tunnel, and you would say, open me a connection to the HTTP service, and then on that connection, which you provide that connection number, you would say, get me index.html. And at the same time, you could open other connections and get other resources. Also, connection 0 is for authentication. The MinimaLT includes something that's like client-side certificates. It's an equivalent, basically, but I won't go more into that. And the multiple connections, can proceed at the same time. Although the precise congestion control details differ a little bit from Quick, which is a new protocol from Google that's very similar. So you might want to Google both of these to get more information about them. Quick seems a bit more interested in that a packet lost that affects, in the beginning doesn't delay parallel resource loading in the end, whereas MinimaLT seems to be more interested in total ordering of all of the packets, even between connections, so that they're totally ordered. But again, see the paper for details. So it wouldn't be a crypto nerd, networking protocol talk without some ASCII art. So I'm just busting that out right now. I didn't have Inkscape at the time that I was making this, and so I did an ASCII art, and I'm like, that's awesome, I'm leaving that. So there are 2 parts to a packet, right? There's the clear text part and the ciphertext part. And the clear text includes your Ethernet headers and your IP headers and your UDP headers. And that's 42 bytes. In addition, there's 16 more bytes. Half of that identifies the tunnel, and half of that is a nonce. Nonce is actually an English word, and I didn't know that. And so it means like the moment, the now, and it's also pronounced number used once. because that's the thing. It's like a number that just keeps on incrementing. And you combine it with your secret so you can prevent replay attacks. That's basically what that's for. And in addition, the first packet includes your ephemeral public key, which, as you can see, is only 32 bytes, which is the wild thing about elliptic curve cryptography. You can have keys that aren't like 2048 bits long. They're only 256 bits long or something like that. So that goes out in the first packet to establish the shared secret, and then later the tunnel ID identifies the shared secret for the server. And in the ciphertext, you include the flow control fields, the sec, the sequence number, and the acknowledgement field. Those are the ones in TCP that allow TCP to be reliable. Reliability is a layer, on top of the protocol of communicating with those fields. So that's actually, that can be done in user space, and that is super rad. I was like, how do you make a reliable protocol? Because I didn't know, and then I saw that it's just layered over this field, and you have this round trip timer, and you estimate how many bytes are in flight, and this is totally something, anybody can hack up and do. And so that's one of the points of this presentation is like, there's room for new protocols, and we can hack them in user space. We can hack them in Node, and we can experiment with different congestion control protocols, and that's a thing, man. That's totally a thing. So after that, so after that, we got the payload, and that's your application data. On the crypto side, the ciphertext is a box, which is a concept from the SALT library. It's a public key system, and so you have a public-private key exchange. Obviously, you keep your private keys, and you exchange your public keys in a way that you establish a shared secret, combine that with a nonce, and authenticate and encrypt the box. So it's completely tamper-proof. It's at a higher level than most crypto primitives. It's built on top of other crypto primitives in an opinionated way by DJ Bernstein and Tanya Lang. So it's like, check, right? But the shared secret is this public key exchange, which takes some bytes, right? Takes this, larger 32-byte key and the 32-byte keys and combines them. So we actually trim, we don't have to send that at each packet. You do that shared secret establishment in the beginning, and then the server associates a 64-bit identifier with that larger shared secret on the server side. That's the tunnel ID. And there's a protocol to sort of change your tunnel ID periodically so that, passive analysis can't track your connection over IP movements. Although if you control the entire internet, like some assholes do, maybe that's a thing. So it's a public key system, and that's the problem, right? How do you distribute public keys? It's just a big old mess, right? So in TLS, as we know, the mess goes like this. Your client knows the address of a DNS provider. The DNS provider gives the address of the server. There's no authentication or anything in that, right? It's a total hackable thing. The client connects to the server directly, and the server gives it, its key, and then the client checks that key against a list of known routes, which is also, a hackable thing. In MinimaLT, it's a little bit different. The client knows the address of the directory service, which is like DNS, and the directory service, the servers register with the directory service. And the client connects to the directory service over a MinimaLT connection because it knows its long-term public key, and makes a MinimaLT query for that server's address and current ephemeral public key. They're ephemeral because they change for forward security. And then it gets that back, and with that information, it can then connect directly to the server without a round trip. I'm kind of breezing through this stuff because I'm burning through time, but the paper is super interesting, and check it out. So I'll skip that bit. For performance, the expensive part of the whole thing is this initial establishment of the shared secret. Like that's the only thing that just costs a lot of resources. And so MinimaLT can do about 8,000 connections per core on a modern x86 system. And extrapolating from some other numbers that they have, I think it's about 750 on an ARM device, although I haven't tried. And then afterwards, it can go quite fast. So why does TCP need a three-way handshake? And why can MinimaLT avoid it? Well, one, in a connection flooding attempt, MinimaLT can force the client to sort of effectively mine for bitcoins. Like, given this secret, produce another value that when combined with it has a hash whose 3 low bits are 0 or something like that. Forcing the client to pay computationally for the ability to connect to the server. And in addition, if you have a request to an unloaded server, and you just give back a response directly. The protocol is designed ideally that the response would be smaller than the request, so you can't use the server's resources to attack a third party. Although that's really the result of this JSConf for me. I was talking with folks, and then I realized, is that right? Are zero round trip protocols actually compatible with defending against amplification attacks? And that's not clear to me. The paper sort of glosses over it, but it's definitely not clear to me, because it's not authenticated when you get a packet that it comes from that IP, because the authentication corresponds to the fact that it comes from this public key, but not that when you reply to the IP that's in the packet, that it will be to the person who sent it. And so if you include a request like get, whatever file in your first packet, you're going to fill up the window, and the TCP window is, 5 or 16 kilobytes or on that order, in your response, which is a pretty big amplification. And I'm not sure, I probably don't understand the things, and this is where I'm not a cryptographer and all this stuff. It's also where the protocol is really new. And in any case, if it is the case that you require a round trip, it's still not a total lose, because you are not worse than TCP in the worst case. And in the best case, where you have a tunnel established already, you don't need that round trip. So in that regard, zero round trip connections are always faster than TCP at any network latency over half a millisecond, which, damn, right? And it always connects faster than OpenSSL, obviously for the round trip time reasons. So very briefly, before I nail this up, this project is new. It's associated with a research project at the University of Illinois, Chicago. And their main thing is not MinimaLT. It's this new operating system called Ethos. It's built on the Zen hypervisor, and it's kind of complicated and new and stuff. And John Solworth's the main fellow, and Michael Patella is doing the MinimaLT part. And MinimaLT is best conceived of for them as a way of, they do typed IPC, inter-process communication, in their operating system. And for them, MinimaLT is a way of transferring that to the remote case. And so I think they're thinking about more authenticated connections between hosts. But in any case, it's a mess, right? Because you got this new operating system, and you got to build it, and it's built with a fork of an old version of Go that doesn't compile anymore. And Linux side as well, you have libraries building for both. And I worked on it, and I wanted to give y'all a node library, but I didn't make it. So I'm getting there, though. I'm getting pretty close. The POSIX API, I think, is going to look more like this. What they do, I'm going to go back a little bit. They have these typed IPCs, but the way to establish these types between the two sides, for me, it's kind of more complication than I care about right now. I'd rather like an API that allows me to just sort of write data on top of a lower level protocol, and I don't have to convert everything to this new API. So that's what I'm working on, should have out soon. And the JavaScript tie-in is that you need an event loop running in order to manage your window and your retransmit times and stuff like that. So libuv is an obvious and awesome thing to think about right there. And you could talk about actually just basing it on salt and other things there, like progressively rewriting parts that are in C right now into JavaScript, like the whole reliability layer. I think that would be super awesome, right? To have the pure JavaScript congestion control running on, authenticated encryption flow control fields. So that would be super awesome. So ending message is that bandwidth's going up, latency staying the same. There's a space for a protocol that offers strong crypto at low latencies. You can, you can lower your latencies by a large percentage. I think it's on the order of 20 to 50% on connections. So it's a new thing. Go forth and hack. The MinimaLT, this is the first presentation about this project anywhere that I know of. And the next one is going to be here in Berlin in November at the ACM Computer and Communication Security Conference. So they're actually presenting the paper, of which the preprint came out in May. So Synac, just say no. I'll be on the Twitters at Andy Wing, and I'll tweet these slides and give an update on the release. So thanks very much.